All right, everybody. Sorry, my recording actually got cut off there. I have to finish this in a different part now. So, got to finish this last example and this fill in the blank stuff here. So, exponential growth. As x increases, the x value, as it increases, then the y values increase. So, growth, which is what we've been talking about so far, like at first, the original definition, if you go back up here, was just that exponential function. So if you look back up here at this box, any exponential function follows this equation. Now we're going to talk specifically about growth, which are the graphs that we just graphed. These are called exponential growth functions. As the x values increase, the y values also increase. So as you look at something like this, as we move towards the right, because that's the positive x values towards the right, then you can see the y values are also going up. That's exponential growth. The only way that happens is if you have this formula, like we talked about, a times b to the x, but b has to strictly be greater than 1. That's only if that number in here is bigger than 1. So if I go back, the b value in this last problem was 2, and that number is bigger than 1, so you see the growth. The domain of exponential functions, if you just look at our last problem here, the domain and range, that will always be the same thing with growth. Exponential growth functions have the same domain all the time. That's all real numbers. The range is always the same as well. That's going to be y is greater than 0. So you just kind of have to memorize that and use it. It's not that difficult. And then before I was talking about the asymptote. Where is that located? Well, that's the place where you cannot cross, which is the x-axis. That will also always be the case. The x-axis here, asymptote. We have one problem left. It's a word problem. Hopefully not going to be too difficult. And you will have to use a calculator for a part of this when you do the word problems. Example 5. When a new species is introduced to a new environment, it often has no natural predators and multiplies quickly. In 1859, 24 rabbits were released into Australia for hunting. The rabbits reproduced so quickly that within 20 years, they were referred to as the gray carpet. I assume because they're gray. We will assume that a single rabbit can populate an average of 3.5 rabbits per year. Now, a lot of people get hung up on the fact that this says 3.5 rabbits per year. I know they don't make a half of a rabbit, but this says it's an average. So if you were to say average 2 rabbits and one had 4 rabbits and one had 3, the average between the two would be, add them together, divide by 2, would be 3.5. So don't get hung up on the fact that it's not saying that rabbits have 3.5 per year. It's the average among the number of rabbits you have. Okay, determine the initial value a. So we're still going back to, now if you want, we can use the f of x notation. Going back to the original exponential function and what it looks like. F of x equals a times b to the x. All we really need is to fill in a number for a and b. And they gave that information in the word problem. So determine the initial a value. So how many rabbits do we start out with? If you look up in the paragraph, in 1859, there was 24. So far, our a value we have is 24. Okay. Determine the growth factor, b. They tell us that as well. How fast are these rabbits growing each year? That's in the last sentence. They populate an average of 3.5 rabbits per year. So our growth factor is 3.5. So what would the exponential function look like for part C? What is the exponential function that would fit the situation? We just plug in a and b into the formula. So we can say it's f of x equals our a value, which is 24, times 3.5 to the x. Now, if you want to use a multiplication symbol, you can. You can also do parentheses. Either one is fine. I probably tend to do parentheses more often than multiplication sign between the two. So that's our function. That's our formula for the exponential function. It's going to be a growth because it's 3.5, which we know is bigger than 1. So it's going to be kind of the same graphs that we've been looking at. Part D, how many rabbits would there be in 1870? Well, we got to figure out how many years that would be. How long has it been? We released them in 1859. So how many years would it be? A lot of people look at this problem and they just want to throw in 1870 into X, but you don't do that. It hasn't been 1870 years since a rabbit's been released. It has only been from 1859. So that would be 11 years. So we don't use that. X would be 11. Because that's how many years have elapsed so far since they were introduced. So just plug in 11 for our X's up here. Both of them. F of 11 equals 24 times 3.5 to the 11th power. Now you can put that in the calculator just as is. If you're using your phone, you may have to do the exponent part first. Maybe I can bring up a calculator. So we can do 3.5 exponent 11, enter. It's pretty big. Then we times that by 24. So it's pretty darn big. It's a lot of rabbits. So we're looking at 23,171,797. 23,171,797. 23,171,797. So that's about how many rabbits there would be in just 11 years. So they're growing pretty quick. That's how many rabbits there are. 23 million rabbits. Okay. Last question of the word problem. What is the first year the population of rabbits will hit over 3,000? Now, we haven't learned how to look at this function up here. We haven't learned how to look at this and determine how many years it would be a certain number. So really we're looking at when is it 3,000? Or when it first hits 3,000, or like when it first goes over 3,000 number of rabbits. So we obviously know it's going to be less than 11 years, and it'll be pretty, like a lot lower than 11 years, because we're at 23 million. So what I would do with this question for right now, since we don't know how to solve it algebraically this way, is just do like a guess and check. How many years do you think it would take? Maybe plug in like 5 and see where we're at. So I can do something like that. And so you would do this on your own as well, like if you had a problem like this on your homework, on the assignment, is we could just plug in 3.5, raise it to the, move it over a little bit so you can see. We'll raise it to the 5th year. That's 525. Then we multiply it by 24. Enter. So 12,605. So it's actually going to be less number of years than that. Maybe let's just try like 2 years. 3.5 to the 2nd power times 24. So it's definitely more. So we're getting closer, right? It's between 2 and 5 years. Let's try 3 years. 3.5 to the 3rd power times 24. So it might be the 4th year. 3.5. This is just something you have to just try. Times 24. So here's when it's first one over 3,000. So it's between 3 and 4 years. So the first year it actually happens, it goes over 3,000, is year 4. So it actually hits 3,000 in between years 3 and 4. So again, that's kind of like this is like a guess and check. For right now. At some point later, I'm not sure if we'll get to it this year or not, we'll be able to figure out how to solve this algebraically so that way we can get the exact number of years. So it might be like 3.75 years or something like that. We can figure out the exact date of when it hits 3,000 rabbits. But for right now, it's just a guess and check, and we know it's between year 3 and 4. 4 is when it goes over, because we got, what, 3,600. But year 3 was a lot lower than that. Okay, so that should be enough to do the assignment now. This is for week 6, I believe. Week 6, yes. And we'll see you next week.